Okay, so I just asked the question. We're doing multi-class classification. I just asked the question, what is a simple form for the prediction rule? If we're just estimating based on the maximum estimated conditional probabilities, we just choose the class with the highest conditional probability. So the first and easiest way to do this is just to notice that the softmax doesn't change the ordering of the components. It just changes the size of the components. And so the max of the softmax is also, or the argmax of the softmax is also the argmax of the arguments. It's not actually the maximum. It is not the same. So the argmax of the softmax is just the argmax of the logit, and we've already said that the probability is equal to the softmax, so we're really just argmaxing the logits, argmaxing the decision function, right? Except for k equals 0, right? Because this is only the argmax over k going from 1 to k minus 1. Otherwise, we have to worry about the 0, alpha 0. And 0 is going to be the max if all of the other ones are negative. So you just have to check if all of the decision functions, other than the first one, are negative. If they are, all of them are, then 0 is the predicted class. Otherwise, you choose the argmax. So that's the thing. And this is consistent with the one versus rest prediction mechanism. Remember, the one versus rest, you trained k different betas, and then you chose the argmax of those k different betas. And then for us, we just set the betas for the 0 class as 0. Okay. So what I'm going to do is illustrate these using the iris data set. So I wrote some scripts to do this, and it shows a little bit of the details of doing this in scikit-learn. So I do a training test split into a 2/3, 1/3 split. The iris data set is not very big, so this is a very small test set. The training set is just 100, so the test set is around 50. Okay, so let's start by training logistic regression. I want to use the multinomial model, otherwise it might use some other method for computing this. And so to do that, I have to choose certain solvers. And I have no penalty for this, no L2, no L1 penalty applied here. So we fit this on the training set. So I want to actually illustrate what the decision boundary is for the decision boundaries for the logistic regression. So I'm going to extract the beta coefficients. These coefficients, it's a 3x2 matrix because there's 3 different classes, and so it gives me 3 different betas. And for some reason, the logistic model here is going to also fit a beta for the 0th component, but it won't change anything in terms of our prediction, and also the intercepts. And then I'm going to draw a line. This is just a quick def I wrote to draw a line for the decision boundary. So if I apply this method, logistic regression, to the iris data set, I get these 3 different hyperplanes, and they're not necessarily, they don't look like good separating hyperplanes. And this is where things get actually really interesting, because our prediction mechanism is just going to choose the argmax of the beta of the decision functions. Really, we just have to think about, of these lines, does a point look more in the positive direction of the normal vector? And we can't see the direction of the normal vectors here. We know it's either in this direction or in this direction. But in this case, you can imagine a very small change in the normal vector of the line can help us do a little bit of a job trying to separate out these 2 classes that are mixed together down here. But a hyperplane that separates that's around any of these hyperplanes would do a great job of separating the red class from the remainder of the classes. And then we just have to see whether it's a little more in this direction or a little more in this direction to decide whether it's which class we're going to predict here. So, as I said, in the way that I presented logistic regression, we don't actually have to fit the 0 class. They do in this, but we could just remove the beta 0 beta from the beta vector, and same with the intercept. That will just zero out all of the betas for the first class. So that's what we see there. And then if we do this, it threw a warning because I tried to plot that line for no particular reason. And we just get 2 of those 3 decision rules, decision functions. Okay. So let's instead use linear SVC, and we're going to use the OVR, which is one versus rest multi-class setting. So we're doing the one versus rest, which remember is going to build k different binary classifiers, thinking of the class as the positive samples and the rest as the negative samples. And we can also extract the betas and plot the lines corresponding to the one versus rest. And this actually turns out to look quite nice, right? So when predicting the reds here from, or separating the reds from the remainder here, this line seems sufficient. It correctly separates the 2. Now, trying to separate the orange or the yellow ones from the other 2 classes is a little bit harder, and you see this hyperplane forms to do that. And similarly for the grays, it's a little bit harder, and we've separated it in that way. Okay. So the SVC I mentioned, it implements the 1 versus 1 setting, although this decision function shape setting says OVR. So I'll come back to that in a little bit. But it does give very different behavior. So the 1 versus 1, what I think this is when I call decision function from this trained classifier, then it will use 1 versus rest for the decision functions. And that's because the 1 versus 1 doesn't give me a way to determine which class it is except through the except through that weighted voting that or the majority voting that I mentioned before. So this is I'm not actually going to, well, I'll be calling this decision function later on when I do ROC curves. But for now, let's just move on. We can still extract the betas, and we can look at the separating hyperplanes, and these are still based on the 1 versus 1 training method. And so we can see one of these. So there's 3 choose 2 different comparisons of the classes, different pairs of classes, which is just 3 of them. So we got 3 different separating hyperplanes, but remember, this isn't a separating hyperplane for 1 versus rest. This is a separating hyperplane for the pairs, for the comparison of the pairs. So we can see this hyperplane here is clearly trying to separate the gray from the yellow. This hyperplane here is clearly trying to separate the red from the gray. And then this hyperplane here is trying to separate the red from the yellow. So that's what we see. Okay. And so I'm going to extract decision functions. We didn't talk about how to extract the decision function for OVO. We just talked about how to make predictions. But we can leave that up. I can leave that up to you to read in the documentation. So what I'm going to do And this is something that's a bit subtle. How do we look at things like ROC curves and PR curves for multi-class classification? Well, the most common way to do this is just to plot a different ROC curve for each one versus rest scenario. So you think of, for each class, that class as being the positives, and then the rest of them as being the negatives, just like in one versus rest training. But then we, if you have a given decision function for that one versus rest, then you can output a score and then plot an ROC curve for that given class. So we're going to start with a 0 class. We're going to extract the ROC curves for these 3 different methods. Okay. So I'm going to, I create this plot, this simple def for plotting the ROC curve, and we see that they actually all do quite well in predicting the class 0 versus the remainder of the classes. And class 0 was that red class. If we go back here, is this red class, and it's easy to separate, so it's not surprising that it does quite well. But then if we go to the next classes, if we plot class 1 versus the rest, this is one of those 2 classes, either the yellow or the gray, and we actually see quite a bit of a difference between the ROC curves here. But remember, these are very noisy ROC curves because there's very few samples in the test set. So I don't know if I would trust the ordering implied here. Remember, with ROC, we like curves that are further up and to the left here. For the OVO training, it does better when we than the remainder of them for separating class 1 from the rest. Whereas for class 2 versus the rest, we actually get somewhat better performance. And these are the grays. And that's partly because the grays had those further out outliers, or just points further that you could separate simultaneously from the red and the yellows. And they all do roughly similarly for this. So you could do something similar with PR curves if you really wanted to. PR, we don't normally think of them in the multi-class setting, just because, remember, precision recall was kind of came from the recommendation system settings, where one of the classes is special, and in the multi-class setting, it's very rare that one of your classes is special relative to the other many classes. So I just wanted to present the ROC, the use of ROC in the one versus rest comparisons.